So in addition to what we've done in the textbook, there's a few extra things that could be on your exam that we need to cover. So these additional notes, we'll look at some of the stuff we've done already, and we'll go through that relatively quickly. And then when we get to some of the more complicated stuff that wasn't covered in our notes, we'll have that as well. So here's a fancy word for counting. In mathematics, the study of counting is called combinatorics. And we've done, our very first thing that we did was the fundamental counting principle. So whenever you have different decisions to make a space for each of those decisions. So here, a new car is being built. You have to make a decision on the colors. So this would be colors, this is transmission, this is interiors, and then you have in each space the number of choices that you have. And with fundamental counting principle, we multiply to get the total. So make your spaces, put your choices in each of those spaces, and then multiply to get the total. Now, something that comes up is sometimes you're allowed to repeat numbers, and sometimes you're not allowed to repeat numbers. So in the cases where you are not allowed to repeat things, it's different than when you're allowed to repeat them. So if you had a 3-digit number, well, this would be 3 decisions. And then we have a choice, how many numbers could go first? So if we're using 1 to 7, you would have 7 choices. Now, if you're not allowed to repeat a number, how many numbers are left? There would only be 6 numbers left, then 5 after that. Multiplying this together would give us 210. With repetition, still 3 decisions, but now it's 7, 7, and 7 for 343. And for example 3, I want you to add that we're going to use, for example 3, 1 to 7, and example 4, we're going to use the numbers 1 to 7. And this is the first one that is somewhat new from what we did in the textbooks. What do we do when there is a restriction? And what are some of the problems that can happen if you don't do it in a certain way? Okay, so I'm going to start off with the problem, because in the problem you would go about like this, and usually we start left to right. So don't write this down. I'll change to red because it's going to be a problem. You'd be like, well, any number could be first. I have 7 choices there. Then I've used up a number, so I have 6 choices left. But now we don't know, because this one says it has to be even. Well, from 1, 2, 3, if I write it out, right, normally you'd say, oh, why don't I put a 3 there? Shouldn't this be a 3? Because there's 3 ones there. But what happens if you used an even number up? Right? In the 7 choices, you could pick any of the 7. You might have used an even number up. You might have used an odd number up, but you don't know. So it becomes a problem if you have a restriction. The strategy is make that decision first. So this is going to be a problem. But if I have a restriction, and always with the restriction, we write the restriction underneath that decision, that has to be even. Well, why don't I do that first? I have 3 even numbers. I choose one of them. That would be 3 choices. So I don't know, maybe I used up the 4. Now how many choices do I have for my first digit? There's 6 left. Then I've used up 2 numbers, then 5, giving 90 even numbers. And again, we're going to, for number 4, just sort of staying, try this one on your own. It's another one with restriction. You can do it exactly the same as we did example 3. But after you get your answer, see if you can figure out a second method that uses both A and B to figure it out. Now, sometimes when I'm on the restriction, I actually write out my choices. It's going to be odd. Does it make sense? There would be 4 choices that could go there. You don't know which one you used up, but you used up one of those numbers. Now from the other 7, there would be 6 left there. Now you've used up 2 numbers, 5 left there, and you get 120 ways. We could also use a new strategy that I'm going to introduce to you called the not strategy. And the not strategy is basically if you can count all of something, and you can count the bad ones or the ones that are not what you want. If you have all of them and take out all the bad ones, does it make sense that everything that's left would be good? This is the not strategy. And in this case, it's not the best strategy because it was super easy to count just with restrictions. But we're going to get into some situations where something's not easy to count directly, and counting the bad ones is way easier. So what does the not strategy say? Well, if we think about all, we did that in part A. All numbers, 7 times 6 times 5, we got 210. Which are the bad ones? Those would be the even ones. We counted that in part 2. There was 90 even ones. And if I took all the numbers and I took out the even ones, does it make sense that you would be left with only the odd numbers and you get 120 that way as well? So this is new for today. Restrictions. We deal with restrictions first. And the not strategy is new. We'll get some more questions with the not strategy as we go. Okay. How many 3-digit numbers, so it makes us think of 3 decisions, can be created using the numbers 0, 1, 2, all the way up to 9 without repetition? This one is tricky because there's a restriction, but the restriction is hidden. Can you see which number has a restriction on it? It has something to do with 0. Is this a 3-digit number? 12. No. We have to be very careful because if the question said codes, like if you have to enter a code to get into your phone or something, you can put a 0 first. That's totally allowed for a code. But if it's a number, we can't have a 0 first. So this first decision has a restriction, and I'm just going to write in here, not 0. Does it make sense? Then we have only 9 choices. How many choices do we have for the second one? 9 again, because 0 gets put back in, but one number was used up. And now 2 numbers are used up for 8. So this gives us 648 total possibilities. This unit is a lot about reading. You have to be careful to read the question because they could ask this same question on the exam but use the word codes, and then it would be 10, 9, 8. But since it says numbers, then you have to think about, well, what does that mean for number? 12 is not a number. It's not a 3-digit number. And so we have a restriction on the first variable. Here's a little warm-up. We've done factorials. I want you to do all 3 of these without your calculator. Come up with a number for the first 2 and come up with a simplified expression for the last one. remember the factorial sign means you keep multiplying down till you get to 1, but you simplify by always expanding the biggest one until you get to the smallest one and say, well, it would keep on going, but that would allow us to cancel, and 7 times 6 is will be 2. Same thing in the second one. Expand the biggest one, which is 10, and you keep on going until you get to 1 on the bottom, which is 6 factorial. And that would cancel out the 6 factorial. Now, 4 factorial, so this is what I'm at. 4 factorial, you get 4 times 3 times 2 times 1. Can you see that the 8 would cancel out the 4 times 2? And I could take the 9 and the 3 and simplify that to be 3 over 1. Try to color code it here so that you can see what's going. So what's left? The bottom is all 1s. So on the top I have 3 times 7 is 21 times 10, 210. And the strategy stays the same even if you're dealing with variables. You have to see which one is bigger. And n plus 2 is bigger than n plus 1. So we start with n plus 2. 1 less would be n plus 1. And we keep going until we get to the 1 on the bottom, which is n factorial. And those will cancel out. So you could leave it either factored as n plus 2 times n plus 1, or if you multiply this out, it would be n squared plus 3n plus 2. And this too is a review. This word, permutation, is when you arrange things and the order matters. And most permutations we can solve with our spaces technique. Like ABC, you'd have 3 spaces, starting with the 3 choices, then 2, then 1. There's going to be 6 total, and if you wanted to write them all, ABC, ACB, BAC, BCA, and CAB, CBA. And we had a formula. This formula is on the formula sheet for permutations. It's connected to spaces right? So if I had 10p2 with the formula, it'd be 10 factorial over 10 minus 2, 8 factorial. With the spaces, it would tell you 2 spaces, start with the 10. So you get 10 times 9. And you might notice in the factorials, if I expanded the bigger one, sure enough, you get 10 times 9 that way as well. So sometimes the spaces are really helpful for seeing an answer quickly, but often on the exam they'll say, make sure you solve it algebraically, and algebraically means you're going to have to use the formula. So we're going to have a couple of those to work with. And here's some special cases. If you had NPN, which means like 5p5 would be 5 spaces, start with 5, should make sense that that's equal to 5 factorial. With the formula, you might remember from the textbook that it's like, why do we need a formula for 0 factorial? Well, we have to have 0 factorial equal to 1, or this situation in the formula doesn't work. So the whole reason 0 factorial is equal to 1 is so that the formula works in all situations. So I would often say that you avoid the permutation formula as much as possible if you can use spaces. Like this one, there's 4 decisions that need to be made. says the order matters, so it's a permutations question. Our next part of the unit will be combinations, where the order doesn't matter, which just, more we learn, like I said before, the more things get complicated. And you would have 10 choices for your first song, then 9, then 8, then 7, and this is equal to 10p4. And of course, that button is on your calculator, so if I go 10, and then I hit the math button and go over to probability, it's the second one, I can type in 10p4 and get that answer that way as well. This one's really easy. If you want to rearrange letters and all the letters are different, it's just going to be 4 spaces, 4, 3, 2, 1. And it's fine if you just write 4 factorial right away. This one's an interesting one because I find it interesting because our brain plays tricks on us in certain situations. And this is a typical situation where your brain might play a trick on you. Okay? 5 people come in for math help. There are 12 desks. How many ways can they be seated if the order matters? Because like sitting at the front is different than sitting at the back. Okay? The number one mistake that happens in this one is a person makes 12 spaces because there are 12 desks. We have to remember that our spaces represent decisions, not containers that things go into necessarily. Students sit in desks, so your brain likes to have that as a container. It likes the spaces kind of as containers. So the number one mistake here is that people would make 12 spaces. But there's not 12 decisions that need to be made. In fact, there's only 5 decisions. Because person number 1 walks in, they have a decision to make. Where are they going to sit? How many choices do they have? They could choose from any of the 12 desks. Person number 2 comes in. Okay? Unless you want to make math help really awkward, you don't sit on somebody else's lap. Right? So now there's only 11 choices left. Person 3 then would have 10 choices, then 9 choices, then 8 choices. And this would be the same as 12p5. So the place where the permutation formula becomes nice is if you were like, well, Mr. Jerry, you have 32 desks in your class. What if 12 people come for math up? Well, that's a lot of spaces and a lot of numbers to write. It might be way faster to write 32p12 than it would be to write out all the spaces. So there's a nice place for the formula as well. Oh, seating plans. How many different seating plans could we possibly have in this class? Well, first of all, if everybody would be here today, we would have 29 people. And what did I say? There's 32 desks, right? So there would be how many decisions, right? There would be 29 decisions, so that's how many spaces there would be. How many choices for the first person? Any of the 32 spots. 32p29. Where if we type this into our calculator, it's going to be, I think, a scary big result. 32 math over probability. 4.3 times 10 to the 34. That is a huge number. And I did this once. I know it was a little bit mean to me, but I did this once. I said, you know what? I'm just going to hit the random thing on the seating plan. I'm going to take out the empty desks. So you just have to worry about these ones that are here. And if anybody guesses the right seating plan, 100% in the course, don't have to come back to class ever again. Just give you 100%. You get it right there. Because look at the odds of getting it. That number is huge. The odds of getting it right are so, I mean, I guess it's possible. So first person goes, they guess first spot, they get the first spot wrong, they're out of the competition. And I do this for a while, and then I don't know, I picked like the 8th person. And they said the first spot, I'm like, yeah. And I pretended all the way through that they were getting it right. Wasn't that mean? But they were completely, I think they didn't even get one right. So. Okay, and I would like you, just so that we're consistent with what we called it in the textbook, switch that to identical objects. Right, this is where we found out there was problems with certain people in class because of their name. Trenton, who's not here today, probably as a result of that class. Right, 2 T's and 2 N's. We call these Mississippi questions because if you're arranging something and there's identical objects, you have to divide out the identical objects. So for in part A, normally 3 letters would be 3 factorial, but you have 2 G's, so we have to factor that in and divide by 2 factorial, which gives you only 3. There's egg, geg, and good. Those would be the only 3 words possible. In Mississippi, well, normally 1, 2, 3, 4, 5, 6, 7, 8, 9. Normally, if they're all different letters, you have 9 factorial. But we have 3 S's, so we have to divide by 3 factorial. We have 2 I's and 2 P's, so we have to divide by 2 factorial for the I's, 2 factorial for the P's. E happens once, the A happens once, so this is good. And sometimes they'll ask you to explain. This is enough of an explanation. The S's, the I's, and the P's. Just so you have an explanation of where you got those numbers from. Sometimes the identical objects are sort of disguised in a word problem. So you have to read the problem and then decide, well, what strategy would I have in this case? How many ways can the houses be arranged? And some of them are identical. So 3 of model A, I can represent those with 3 A's. 4 of model B, and 2 of model C. This is like a Mississippi question. We have identical objects. So normally, if they're all different houses, it'd be 9 factorial, but we have 3 A's, 4 B's, and 2 C's. You can type this into your calculator to figure out the answer. One thing I would suggest though, okay, you have the fraction button, make sure that you use it. So I'm going to go to 9 factorial, so I have to hit the math button and go over to probability, and number 4 is factorial. One thing I'd recommend is some of the smaller factorials, since it takes so long to hit that exclamation mark, maybe we remember that 4 factorial is 24, 3 factorial was 6, and 2 factorial was 2. That makes it go a lot faster for calculating things in your calculator. So you get 1,260. Some other shortcuts for you. I keep hitting the math button, but you know the shortcut for fractions, there's also alpha y equals a shortcut for fractions. You go over as a shortcut for functions, and number 9 has the factorial button there as well. Might be a little bit quicker. So we did a question very similar to this one in our notes. John lives 3 blocks north and 9 blocks east of school. So I'm going to draw a grid here. And on this grid, he lives northeast, so northeast, this is his home right here. So that means his school is right there. He is walking home. How many different ways can he get home if he always I showed you two different ways to do this. If he's always going from school home, he's going to have to go north 3 times and east 6 times. Neat. Yes. Now, this is a Mississippi question, so if we rearrange the north and the east, we would get the total ways that we could go. And I showed you could also do this by counting. So we could, starting here, say, each of these points, we could count how many ways you could get to each point. And again, we're assuming John is always getting closer home. So each of these ones straight along will all be ones, because even this point over here, there's only one route to get there, which is straight east, without doing a backtrack. So those will all be ones. But then as soon as you can get to, like I can get to this dot via this route or via this route, I add those two together, which gives me 2. 2 plus 1 is 3, 3 plus 1 is 4. So I can fill in these numbers, 4, 5, 6, 7, 3 plus 3 is 6, 10, 15, 21, 28, 10, 20, 35, 56, and 84. And if you would type in 9 factorial over 3 factorial, 6 factorial, that would give you 84. Now we could take this question where we get to restrictions. We could take this question and add some interesting details. I'm going to erase this and say, okay, John is walking home, but now has to go past Julie's house every time he walks home. Now how many ways can he get home if he has to walk past Julie's house? Well, this is a restriction added on here. Do you see that? I'm going to take out, yeah. You see that this section here is no longer, you'll never go through those ever again. As a result, those will all be taken out. So now if we would do our counting, well, these are the dots he could go to, right? Green one, and then those ones. So one path there, one path there, one path, one path, one path. 2 paths, 3 paths, 4 paths, 5 ways to get to Julie's house. Now what about these next dots? Can you see that there's only, from the green dot, only one way to get to this dot? Because there's this orange part is blocked off. This will be 5 and this will be 5. Because it's basically 5 plus 0, 5 plus 0. This one is 5 plus 0. This one's 5, and this one's 5. Then this would be 10, 15, 15, and 30. So now there would be 30 ways he could walk home if he had to go past Julie's house. Then Julie is complaining, because she's like really annoyed. So now there's restrictions put in place, and now John has to walk home, and he's not allowed to go past Julie's house. How many ways can this be done? That would be a not strategy. We counted 84 was all the ways. 30 are the bad ways. Does it make sense then that if he was not allowed to walk past that place anymore, there would be 56 ways that he could get home by not going to that spot? Or you could just recount this by taking these away, right? Erase the numbers. We could recount it, but now put a big orange spot here. That's not allowed. And do the numbers this way, and you would get 54 as a result. Okay. Another new restriction that we haven't done before is called the grouping strategy. Sometimes you're wanting to arrange things, like on a shelf, or, different, arranging things on the shelf is probably where this most often comes up. Maybe you're arranging books, you're like an avid reader, and you're like, but I want to keep certain genres together. Or maybe you're arranging all of your stuffed animals from when you were a kid on a shelf, and you want to keep like the Beanie Babies together, and the Webkins in another spot. I don't know. I don't know what kind of stuffed animals you had as a kid. So this becomes a grouping strategy, and the strategy for the grouping strategy is you count how many groups you have and do the number of groups factorial first. Then you arrange each group. So here's the example I have. Let's pretend I'm arranging math books on a shelf. Seems plausible, okay? But I want to keep my calculus books together, I want to keep my algebra books together, and I want to keep my geometry books together. So how many ways can I arrange them? Well, the first thing I realize, my first decision is how many groups do I have? 3 factorial. So I'm going to decide, am I going to go calculus, algebra, geometry, or calculus, geometry, algebra? There's going to be 6 ways just by deciding which groups are going to be. Then after I've decided which group is first, which group is second, which group is third, then I go to each of those groups and start off with calculus. In the calculus group, there's 4 books. So that can be arranged in 4 factorial ways. Then in the algebra group, there was 5 books. And finally, in the geometry group, there was 4 books again. And since each of those are decisions, we would multiply that all together. 3 factorial times 4 factorial times 5 factorial times 4 factorial. So whenever you want to put things together, that's grouping them, okay? Whenever you have the same object repeated, that's identical objects. Sometimes people get the grouping strategy and identical object strategy mixed up. So here's a grouping strategy with people. 5 people are wanting to go sit at the park bench, and Jill and Bill want to sit together. Aww, springtime. So, how many ways can this be done? Well, we have first to decide how many groups there are. And we have to be careful here, because a lot of people will say there's 2 groups. There's Jill and Bill, that's one group. But Amy, Lee, and Tom, do they have to be together? No. You just want Jill and Bill to be together. Jill and Bill could be together in the middle, right? Amy, Lee, and Tom could be on the outside, right? So when we're thinking about groups here, we're going to have 4 groups. Sometimes people think of this one as, well, maybe Jill and Bill are together all the time, that you start thinking of them as one person. You've probably seen maybe couples in the school are like, are they ever apart? And so now instead of thinking them as two people, they're now just commonly known by the collective of the Jill Bill. There goes the Jill Bill, because you never see them apart. So then the number of groups is like, well, how many people are there now? There's only 4 people. There's Amy, Lee, Tom, and the Jill Bill. How many ways could you put 4 people on a bench? There would be 4 factorial ways. But it's a grouping question, so then you look at each individual group and arrange them. Well, the Jill Bill could be the Jill Bill or the Bill Jill. So there would be 2 factorial, if they decide whole left hand, or right hand, left hand, we're not quite sure. So there would be 2 factorial ways you could arrange them. You would not have to do the other ones. Like, if you did spaces, it's like, well, 1 factorial, 1 factorial, 1 factor for Amy, Lee, and Tom. That blue part you wouldn't have to write down because it's just multiplying by 1 after the fact. The only thing that makes a difference is the 4 factorial, which is 24, times the 2 factorial, which is 2, and we get 48 ways. Okay. Part B. Uh-oh. Things are spreading. Now, Jill and Bill and Lee and Amy have to sit together. Poor Tom. Don't worry. Tom gets his revenge in part 3. Okay. So now, how many groups do we have now? Well, there's the Jill Bill and the Amy and Tom. This is a group. This is a group. We would have number of groups or number of people, 3 people or 3 groups now. How many groups are bigger than 1? Well, the Jill Bill group, 2 factorial. The Amy group, 2 factorial. And poor Tom. We don't even have to include it. Surprised he went to the park bench. Anyways, I'm surprised they all go to the park bench in part C, but we'll talk about that when we get there. So now 3 factorial is 6 times 2 is 12 times 2 is 24. 24 ways. Now in part C, in part C, something happened. I don't know how it involved Tom, but something happened and Jill and Bill refused to sit together. I'm surprised the 5 friends still go to the bench together. Lee and Amy they can sit together, but they don't have to, so we're not worrying about them in part C. We just want to make sure that Jill and Bill do not sit together. And this is a great example of where to use the not strategy. The not strategy, again, is, can we count all of them and minus the bad ones? So all of them would just be 5 people sitting in the park bench, 5 factorial ways. No restrictions whatsoever. But the bad ones we counted in part A. In part A, we counted that there was 48 ways that Jill and Bill were sitting together with the grouping strategy. Does it make sense if you take all of them and take all the ones where they're sitting together, the ones that would be left would be all the ways that they're not together. So this is 120 minus 48. Gives us 72 ways. You will also start to notice that certain strategies start to get overlapped together. So this was using the not strategy with a regular permutation and a grouping question, all built together in one question. And the last strategy that wasn't in your textbook is called cases. Sometimes you can't count something all together all at once. Then you use a cases strategy where you break up your question into smaller, doable things, count those all separately, and in the end, add it all up together. Sometimes we see cases questions when they have things like this. At most, 3 different digits. So we have to break this question up because we could count 3 different digits, or 2 different digits, or 1 digit, and they'd all be considered. So what we do in a cases question is we actually write out case number 1 and describe what we're going to count. I'm going to count my 3-digit numbers, so I would have 3 decisions to make. It's a number question, so we have to be careful here because there is a restriction that your first one is not a 0, giving you 9 choices, then 9, then 8, which we counted earlier was 648. In cases, what haven't we counted? We haven't counted 2-digit numbers. So now it would be 2 spaces. Again, a restriction on here that this is not 0. 9 choices there. 9 choices because you've used up 1 number, but 0 can get put back in. And case number 3. 1-digit number. Is there a restriction on 1-digit numbers? No. You could have any 10, because 0 is a number, and it does have a digit. And then in a cases question, after you've done all of your cases, you add them up to get your total. 648 plus 81 plus 10 gives us 739 in total. So there are times when we can't add things up directly, we have to split them up. And one of the greatest examples is when they say at most this many numbers or at least this many numbers, because you have to have, well, it could be 4 numbers or 5 numbers. And probably the most, or one of the most unique places that a cases question comes up is with restrictions, but you actually have 2 restrictions at the same time. So we want things to be greater than 300 and even. Why? I'm going to switch to red because I'm going to start by doing it without cases and run into a problem. This number has to be even, so when I go here, that would give me choices of 2 and 4. And it has to be bigger than 300, so that gives me choices of 3, 4, and 5. And the restriction strategy says, deal with your restriction first. I have 2 of them. Okay, well, let's say I do this one first. I have 3 choices. How many choices do I have for the last one? 2? But what if I use the 4? If I use the 4, then I only have 1. If I didn't use the 4, then I have 2. Should I just take the average and write 1.5? No, we have a problem. We have a problem because we have a restriction and it overlaps. If the restrictions didn't overlap, you would be fine. But the problem here is that we have a restriction that overlaps. So what we do is we break up our restrictions into cases. And you choose whichever restriction you want. I usually choose the restriction that has less options. So the last number is a 2 or a 4. Case 1, I'm going to count all the ones that end in a 2. So I'm saying this has to be a 2, only 1 choice. If I ended with a 2, I go to my other restriction. What are the possibilities for my other restriction? Well, it still can be all 3 of them, right? The 2 didn't affect that. There would be 3 choices there. how many choices do we have for the number in the middle? Okay, we started with 5 numbers. You've used up 2 numbers. We would have 3 numbers left, giving us 9 ways. Case 2. What haven't I counted? Well, I was breaking up my last restriction. It could have ended in a 4. If it ended in a 4, so this is a 4 here, 1 choice. Now when I go to my first restriction, it can only be a 3 or a 5, because the 4 is already used up. 2 choices there. You've used up 2 numbers. How many choices left in the middle? 3. 2 times 3 times 1 is 6. Add your cases up, and you get 15 ways. This would work if you decided to break up the first restriction. You could have said, start with a 3, start with a 4, start with a 5. Or sometimes people say, start with a 4, because that causes a problem with the last one, and then start with a 3 or 5, and have 2 cases that way as well. So when your restrictions overlap, as these ones do here, then we have a cases question. Another very typical cases question, I'll have one of these on your first take-home quiz, and I'm pretty sure I have one on your test as well, is a question that says, can you use we're still only using 1, 2, 3, 4, and 5. Sorry, my original question, how many 3-digit numbers can be formed using that are greater than 232? Why is this a cases question? And again, I'll take up my red pen. You have a restriction on the first digit. 2, 3, 4, or 5. But if I would do this, pick 4 numbers here, then I have an issue with the second one. Because how many numbers do I have left? I have 4 numbers left, unless I pick the 2. Because if I pick the 2, it has to be bigger than 232. So I run into a problem by trying to do it directly. Because I don't know what number I can put. Because the number that I want to put in that second decision is dependent on what I chose in the first one. And anytime it's dependent on that and you can't do it directly, we have to use cases. So, systematically how I like to do the cases here is I start with my first restriction. And I think, what would guarantee that I wouldn't have to worry about my next decision? Can you see that only the 2 is the problem? If you started with either the 3, the 4, or the 5, that would count numbers in the 300s, 400s, and 500s. No matter which numbers I count in the 300s, 400s, and 500s, they're guaranteed to be bigger than 232. So when I go to my decisions here, and say I'm starting with here a 3, a 4, or a 5, 3 choices, there are no more restrictions on the other digits. So I started with 5 numbers, I've used up 1, there'd be 4 numbers left for that. I've used up 2 numbers, there'd be 3 numbers left here, giving me 36 numbers in the 300s, 400s, and 500s. Next, case 2. What haven't I counted? I'm going to start with a 2. 1 choice. Then I'm not done here. Now I look at my second digit, and I'm like, ooh, the 3 is going to cause a problem here. So what would guarantee that it's bigger? If I started with a 2, I'm not going to worry about that 3 right now. but then put a 4 or a 5 next. We're now counting numbers in the 240s and 250s. They're guaranteed to be bigger than 232. So if I put 2 choices here, there would be no restrictions on my last digit. How many numbers do I have left? 3. Case 3. What haven't I counted? Now I have to put that, start with 2, then the 3. So this has to be a 2, 1 choice. This has to be a 3, 1 choice. Does that mean we'll have restrictions on our last one? It has to be bigger than 232, so I can't put 1 in there. I've used up 3 and I've used up 2, so my only options that are left, there is a restriction on this, so I'm going to write them down. And this is where writing your options down help you see that you might want to put a 3 in there, but you're not allowed to. There's only 2 choices left. And if we add up all 3 of these cases, we get 44 weights. So this is a very typical cases question where they say, we want to have numbers bigger than this. You're only allowed to use these 8 numbers. How many ways can that be? And I'm going to have one of these on your quiz. I think I'll give you a take-home quiz tomorrow. And then tomorrow we'll start combinations. We'll end the video here.